Hello, welcome to another module in this massive open online course. So, in this module let us start looking at another new aspect, that is quantization. Alright. So, we will start looking at a new aspect in this module, that is quantization. Okay. Now, what is quantization? Remember, we already know sampling, that is we are sampling signals at discrete time instants, correct. So, we have the signal and which we are sampling at the sampling instance, the multiples of the sampling instance, that is, this is the sample at m and ts at the nth multiple of the sampling. Now, this sample can still take, this is can take any analog value, okay, can take any continuous so the sample that we have sampled of the signal, the sample can take any value, alright, can take any value on a continuous scale, alright. And so, we want to, for the purpose of digital communication, we want to convert it to a discrete set of values, that is belonging to a discrete set, so that we can convert it into discrete information bits, and these bits can then be subsequently transmitted over the communication channel, or they can be stored, alright. So, the purpose of converting these samples which can take values from a continuous set to values from a discrete set or to levels from a discrete set is termed as quantization. So, converting this continuous valued samples, conversion of these continuous time values to a discrete, or mapping these samples to a discrete set of values is termed as this is termed as quantization. Okay, converting these samples, this continuous samples which have continuous values, to a discrete set of values or a discrete set of levels is termed as, this process is termed as quantization. Okay, and okay, and so the purpose of quantization, I already said, the purpose of quantization is to eventually is to convert these samples to a to information bits, okay, that is important, to binary bits, okay, information bits which can be stored or transmitted, which can be stored, these can be stored, these information bits can either be stored or transmitted over the channel. Over the digital communication channel, alright, they can be transmitted over a digital communication system or can be stored in a digital storage device, alright. And therefore, this process of quantization can be represented as follows. Now, we have the sample m. So, m is a sample, we have the quantization function gm. So, this maps it to nu. So, this is the sample which can take any particular value. So, this is your sample, this is your quantization function, this is your quantization function, and this is a quantized, this V belongs to a quantization set. V is belongs to a discrete set of values which are also termed as the quantization levels. So, we have this quantization function G. So, our quantizer, so our M is the sample to be quantized, G is the quantization function, and V is the output of the quantization function, and V, this output V belongs to a discrete set of values, also termed as the quantization levels, that is this discrete set of values are termed as the quantization levels. So, the quantization can be fixed as Gm equal to Gm, the quantizer output. Okay, G is also the quantization function, can be termed as a quantizer equals Vk. This is the kth quantizer level, if Mk less than or equal to, we can say Mk less than or equal to M less than or equal to less than Mk plus 1. So, we can say that this quantizer, okay, this quantizer comprises of levels V1, V2 up to Vn such that if the sample M, right, the sampled value M lies between Mk and Mk plus 1, it is quantized to the quantization level, right. The quantizer output is Vk. Alright, so V1, V2, Vn are the discrete set of quantization levels or the discrete set of outputs of this quantizer. Okay. So, let us look at some examples of this quantizer. A simple quantizer is what is known as a uniform quantizer. One of the simplest quantizers is known as a uniform quantizer. This is one of the simplest quantizers, which is a uniform quantizer. As the name implies, a uniform quantizer simply means that the quantization levels are uniformly spaced. So, the quantization in a uniform quantizer, as the name implies, the quantization are the quantization levels are uniformly, these are uniformly spaced. For instance, let us consider a 5 level quantizer example. Let us consider a 5 level quantizer. Okay, so which means there are 5 quantization intervals and correspondingly there will be 5 quantization levels. Okay, so let us say the quantization interval is of width delta. So, there is one interval from delta by minus delta by 2 to delta by 2, another from delta by 2 to 3 delta by 2, 3 delta by 2 to 5 delta by 2 to minus 3 delta by 2 minus 5 delta by 2. Okay. And now, between minus delta by 2, if M lies between minus delta by 2 to delta by 2, it is mapped to 0. If M lies between 3 delta by 2 to delta by 2, it is mapped to delta. If M lies between 3 delta 2 by 2 to 5 delta by 2, it is mapped to 2 delta, that is the output is mapped to 2 delta. Similarly, if it lies between minus delta by 2 to minus 3 delta by 2, it is mapped to, output is mapped to minus delta. If it lies between minus 3 delta by 2 to minus delta by 2, it is mapped to minus 2 delta. This is minus 2 delta. So, we have, as you can see, we have, let us look at this quantizer again. We have, well, 5 quantization intervals. The 5 quantization intervals are minus 5 delta by 2 to minus 3 delta by 2, minus 3 delta by 2 to minus delta by 2, minus delta by 2 to delta by 2, delta by 2 to 3 delta by 2, 3 delta by 2 to 5 delta by 2. Okay. So, these are your 5 quantization intervals. Okay. These are 5 quantization intervals, and we are calling this as a uniformly spaced uniform quantizer, because note that the widths of these quantization intervals are uniform. Each quantization interval is of width delta. For instance, you can see 5 delta 2 by 2 minus 3 delta by 2 equals. So, you can see each quantization interval, all the 5, each quantization interval is of width. Each quantization interval each quantization interval is of width delta. Therefore, this is known as a, this is termed as a uniform quantizer. Each quantization interval, all are of the same width delta, that is all are of same width delta or uniform width delta, hence termed as a uniform quantizer. As a hence this is termed as a uniform quantizer. Okay, that is the first point. So, therefore, this is termed as a uniform, therefore, this is termed as a uniform quantizer. Okay, that is the first point. Now, the second aspect is that, now if you look at the quantization level, for instance, if you look at the quantization level in 3 delta by 2 to 5 delta by 2, quantization level is the midpoint, alright. So, for instance, in each quantization interval, correct, in each quantization interval, the quantization level is the in each quantization interval, the quantization level is the midpoint of the interval, alright. It is not necessarily always true, this is only true because this is a uniform quantizer, that is in each quantization interval, alright, in each quantization interval the quantization level is the midpoint of the interval. For instance, in 3 delta by 2 to 5 delta by 2 it is 2 delta, in delta by 2 to 3 delta by 2 it is delta, alright, which means that if the signal sample lies between m, that is m lies between 3 delta by 2 to 5 delta by 2, alright, it is quantized to 2 delta, alright, it is mapped to 2 delta. So, which means the quantizer can be described as follows. If for instance, let us say 3 delta by 2 less than or equal to m less than 5 delta by 2 G of m is equal to the midpoint, that is 2 delta. Similarly, if delta by 2 less than or equal to m less than or equal to 3 delta by 2, G of m is equal to the midpoint. If minus delta by 2 less than or equal to m less than delta by 2, Gm is equal to minus delta. Similarly, if minus 3 delta by 2 less than or equal to m less than minus delta by 2, Gm is equal to minus, this in this case Gm is equal to 0, minus delta by 2 less than or equal to m less than or equal to delta by 2, it is the midpoint 0. If minus 3 delta by 2 less than or equal to m less than minus delta by 2, Gm is equal to minus delta. Finally, if minus 5 delta by 2 less than or equal to m less than or equal to minus 3 delta by 2, then Gm is equal to minus 2 delta. Alright. So, this is the your basically the representation of the, this is basically the overall representation of the quantizer. Alright. Now, you can observe that this quantization characteristic for all signal samples, right, that lie between for instance 3 delta by 2 to 5 delta by 2, all these samples are mapped to the quantization level delta, which means it is a many to one mapping, right. You can see an infinite set of values belonging to belonging to 3 delta by 2 to 5 delta by 2 are mapped to 2 delta, right. So, therefore, it is a many to one mapping, it is a lossy mapping, alright, and therefore, by definition there is going to, because you are mapping an infinite set of values to a representative finite value, alright, there is going to be an error in the way, alright. For instance, if m is exactly equal to 2 delta, when you map it to 2 delta, there is not going to be an error, but if m is for instance let us say 5 delta by 2, okay, and you map it to 2 delta, then you are going to incur a quantization error of delta by 2. Alright, and you can see depending on where it lies in this quantization interval minus 3 delta by 2 to 5 delta by 2, you can incur a quantization error that lies between minus delta by 2 to delta by 2. Alright. So, this quantization error, for example, all values in 3 delta by 2 to 5 delta by 2 are mapped to 2 delta. Therefore, there is going to be a quantization error. Therefore, this is a, first of all, this is a many to one mapping, that is the first point. Second, there is going to be a quantization error. By definition, there is going to be a an error. This is a many to one, therefore, it is a non-invertible mapping. This is termed as quantization error. This is termed as quantization error. For instance, correct. For example, if m is equal to, let us say you have your 2 delta plus delta by 4, that is 9 delta by 4, then m you can see lies between 3 delta by 2 to 5 delta by 2. Therefore, m is mapped, correct, m is mapped to 2 delta, which means the error, therefore, therefore, there is a quantization error, and the quantization error is 9 delta by 4 minus 2 delta, which is equal to delta by 4, alright. And therefore, depending on where the sample lies between 3 delta by 2 to 5 delta by 2, the quantization error can range from minus delta by 2 to 5 delta. If the sample is minus 3 delta by 2 to 2 delta, then of course quantization error is the quantization error is 3 delta by 2 minus 2 delta, that is basically the original sample minus its quantized value, correct. Remember how we are calculating this quantization error, that is the original sample value minus its quantized value. So, 3 delta by 2 minus 2 delta, that is minus delta by 2. If it is 5 delta by 2, alright, 5 delta by 2 minus 2 delta, that is delta by 2. So, depending on where it lies in the interval, the quantization error can range from minus delta by 2 to delta by 2. So, for example, so depending on where it lies in the interval, depending on where it lies in the quantization interval, the quantization error can range from minus delta by 2 to delta by 2, okay, that is the first, that is another point, okay. So, quantization error lies in the interval minus delta by 2 to delta by 2. Now, the other thing that you can observe is the maximum, since the interval, the total quantizer can take input from minus 5 delta by 2 to 5 delta by 2, alright. So, the minimum sample value can be minus 5 delta by 2, maximum sample value can be 5 delta by 2. This is termed as the dynamic range of the quantizer, okay. You also notice from here that minimum sample value equals minus 5 delta by 2, the maximum this minus 5 delta by 2 to delta by 2, this is termed as the dynamic range of the quantizer. Alright. So, which means that the quantizer can take only values of samples from minus 5 delta by 2 to 5 delta by 2. So, therefore, when you design a quantizer, one has to take this into account, what is the range of the sample. So, naturally the samples, the total range in which the samples lie has to be captured, correct, by the dynamic range of this quantizer. Alright. So, they have to be captured by the dynamic range of the quantizer, okay. So, that is this minus 5 delta by 2 to 5 delta by 2 can be considered as the dynamic range of the quantizer, okay. So, can be considered as the dynamic range of the quantizer. And finally, so you can see that you can see various aspects, each interval is of width delta, correct. Of width delta, quantization level is the midpoint of the interval quantization level equals the midpoint of the interval. And further you can see one more point, that is when there are odd number of levels, there is going to be a quantization interval from minus delta by 2 to delta by 2 and which corresponds to the quantization level 0. So, there is going to be a quantization level corresponding to 0. This is therefore termed as a mid-tread quantizer, because in the midpoint of the quantizer, the quantizer function, which is also termed as the quantizer characteristic, is flat. This is termed as a mid-tread quantizer. So, we have a flat quantizer characteristic at midpoint at midpoint this is termed as a mid-tread quantizer. Okay. So, at midpoint the quantization characteristic is flat, this is termed as, that is basically between minus delta by 2 delta by 2, it is mapped to 0, this is termed as a mid-tread quantizer, alright, and this mid-tread or quantizer is arising because there are an odd number of quantization levels, okay, and this is arising because there are an odd number of quantization levels, okay, arising because there are odd number of quantization So, odd number of quantization levels implies that it is a mid-tread quantizer. Okay. So, odd number of quantization levels remember we have 5 quantization levels, odd number of quantization levels implies we have a mid-tread quantizer, which implies midpoint of quantizer, the characteristic is flat, that is midpoint, not the midpoint of quantizer, basically the midpoint of the dynamic range, that is if you look at the dynamic range minus 5 delta by 2 to delta by 2, 5 delta by 2 at the midpoint, at the middle of the quantizer, the quantization characteristic, right, the quantization characteristic is flat, that is it is basically mapped to the 0 between minus delta by 2 to delta by 2, the quantizer level is 0, this is termed as a mid-tread quantizer, alright, you can say midpoint of the quantization characteristic or midpoint of the dynamic of the quantizer the quantization characteristic is, the quantization characteristic is flat, this is termed as a mid-tread quantizer, this is termed as a mid-tread quantizer, okay, this is termed as a this is termed as a mid-tread, this is termed as a mid-tread, this is termed as a mid-tread quantizer. Okay. So, what we have seen in this module, we have seen an introduction to basically the concept of quantization, alright. We have seen what is the definition of quantization. Quantization basically maps the continuous valued sample of the signal to a set of discrete values or quantization levels, alright. This is termed as quantization, alright, and there can be different types of quantizers. One of the simplest type of quantizer is a uniform quantizer, which consists of a certain number of levels. Each of them have all of the with the uniform quantizer is characterized by uniform spacing of the intervals. All the intervals of the uniform quantizer have an equal width, alright, and the quantization level corresponds to the midpoint of the level of the interval. Okay, and we have seen that when the uniform quantizer has an odd number of quantization intervals or corresponding to an odd number of quantization levels, the midpoint of the quantizer, alright, the midpoint of the quantizer is flat. This is termed as a mid-thread quantizer, and more importantly, the quantizer, not just a uniform quantizer, any quantization characteristic is a many to one mapping, because all the sample values belonging to an interval are mapped to a single value, that is the quantization level. So, naturally this is a many to one mapping, which means it is not invertible, it is a lossy mapping, alright. So, once you have your quantization level, you cannot recover the original sample from that, because it is a many to one mapping, okay. So, therefore, there is going to be a quantization error, alright, and this quantization error, naturally depending on the width of the interval, the width of the interval is large, then a large number of samples are mapped to a single value, therefore, the quantization error is going to grow. Alright. So, the finer the quantization intervals, that is the finer the interval, that is the smaller the quantization interval, the smaller is going to be the quantization error, because the quantization error, remember, minus delta by 2 to delta by 2 in this case is basically proportional to delta by 2 to minus delta by 3, it is proportional to the width of the quantization interval. Therefore, you can say that if you want to reduce the quantization intervals to make it more accurate, you have to make the quantization interval small, but if the quantization interval becomes smaller for the same dynamic range, then you are going to be a large number of quantization intervals, which means large number of quantization levels, which means you will need a large number of bits to represent the quantization levels of that quantizer. So, that is the trade off, it is the quantization error versus the bit rate of the quantizer, alright, which is the number of bits that are required to represent the levels of the quantizer, alright. So, we will look more at this in the subsequent lectures or the subsequent modules. Thank you very much.